So hi everyone, I'm Ava and I'll be presenting on how to reduce attack surface via service control policies or SCPs in a multi-account AWS environment and discussing lessons on how my team was able to do this at Stripe. So to introduce myself, I work at the cloud security team at Stripe. Previously, I was a software engineer in AWS for AWS Security Hub and the quantum computing service, Amazon Braket. So about my company, Stripe's mission is to increase the GDP of the internet by making it easy for any business to accept payments online. And so due to the sensitive nature of the data that Stripe processes, one of its top priorities is security. And as for my team, our mission is to prevent and detect insecure cloud configurations and design and enforce security invariants in our cloud environments. For example, in addition to this project on reducing cloud attack surface, I also work on creating tooling that helps us detect and auto-remediate misconfigured cloud resources. So today I'll be talking about how we dealt with the problem of having to ensure security for our multi-account environment, where the attack surface is extremely wide with over hundreds of services and over 25 regions available to use. We'll be discussing the available AWS tooling for addressing this problem, how we formulated Allowlist policies of approved services and regions that dramatically reduced the attack surface we had to secure. Also, how we deployed these policies safely, how we maintain these policies over time, and our lessons learned in the process. So first, the problem that we want to address is how to secure this broad attack scope. So this surface, this AWS environment by default allows more than 250 AWS services and over 25 AWS regions. And so here we have a diagram, which is a periodic table representation of a selection of AWS services. As you can see, the number of services is overwhelming, and each AWS service, such as S3, has a wide range of configurations and insecure settings, such as allowing anyone to read or write to an S3 bucket. With such a wide attack surface, it's difficult to have controls or detections over every AWS service. Even if you have two-party approval for infrastructure deployments, they may still make a mistake in configuration, especially when there are some resources such as Redshift clusters, which are public by default. And furthermore, for such a large number of regions to stand up infrastructure, sometimes you may end up with different levels of security amongst AWS regions. This can happen since teams often need to explicitly build infrastructure to add controls or enable monitoring and detection in new regions. And additionally, sometimes AWS features may not even be available in certain regions, which makes building security infrastructure in every region even more difficult. And finally, as a company grows, it has more and more engineers supporting various parts of the infrastructure, and access to the cloud environment also grows, making it more likely that a cloud resource is configured insecurely. Therefore, it's imperative that we have an automated solution for securing our cloud environment, especially as the number of deployments and the size and complexity of the infrastructure grows. So the approach we'll be discussing today is to decrease the size of the environment that needs to have controls and detections by only allowing access to the services and regions that are used and approved through centrally controlled policies. As you can see, this reduces the set of configurations and services we have to worry about, And instead of the allow by default paradigm, we switch to the deny by default paradigm. With the solution of reducing the attack surface in mind, we can discuss the AWS tooling available and how to use this free tooling to centrally restrict access. So the main AWS service that we'll be using is AWS Organizations. It's a free service for centrally managing and governing multiple AWS accounts. And so first of all, I'd like to answer the question of why we use multiple AWS accounts instead of just one, and hence why we use AWS Organizations to govern these multiple accounts. So each account is a collection of cloud resources and acts as an isolation boundary. Sharing data and resources must be explicitly allowed between accounts. Accounts can be organized into organizational units or OUs. So for example, this tree diagram represents an AWS organization starting from the root at the top. Each yellow block represents an organizational unit or a grouping of accounts or smaller OUs. The benefits of the multi-account approach are multifold. It can help drive towards least privilege by using accounts and their strong isolation boundaries to group workloads and apply distinct security controls. It can help limit the scope of impact for incidents. For example, if an attacker gets admin credentials for an account with a portion of your AWS resources, that's much better than if they get access to an account with all of your AWS resources. AWS accounts also have hard limits on how many resources it can support, such as the number of S3 buckets and IAM roles, as well as rate limits for AWS API calls. This restricts how large an AWS account can become. And finally, the multi-account paradigm is a best practice strongly recommended by AWS for both security and reliability purposes. Here's an organizational structure that's very similar to what we adopt at Stripe and what AWS recommends. The guiding principle for organization is to group by function or common set of controls. For example, here we have a sandbox OU for an isolated environment with minimal controls for experimentation that teams across the company can use. We also have an acquisitions OU for new AWS accounts for companies that we acquire, which may be used to a different set of security controls than the main company. Finally, we have the main OU that's divided into security, infrastructure, and services. Each OU is then further divided into pre-production or production accounts, and this will later help with the incremental deployments of controls. The organizational structure is the foundation on which we'll build our access control policies. AWS Organizations also offers the ability to implement service control policies or SCPs. An SCP overrides all other access control policies and restricts permissions for IAM roles and users, including root users. It can be attached to an account, an OU, or the root, which is all accounts in the organization. And thus, it allows central access control management from the root account of the organization. In the example here, if we have an SCP which denies, in the example here, we have an SCP which denies the ability to leave the organization. So if someone were to call the API to leave the organization, they would get an access forbidden error. And we'll write our policies to reduce the attack surface using these SCPs. So now that we understand what an SCP is and how it restricts access across a multi-account environment, let's move on to how we formulate the control policies that will by default only allow the AWS services and regions that are used, decreasing the attack surface. Here's an example of a service Allowlist SCP. Notice that the effect is allow, and in the actions field, we have the list of AWS services that are allowed, like Access Analyzer, EC2, S3, and so on. Next, we have the region Allowlist SCP, which in plain English means that all API calls action star in a region that's not in this list are denied with access forbidden. So now that we have the format for these SCPs for allow lists, we can talk about how we organize the allow lists among the accounts in our organization. So one option is to have a global allow list for all accounts at the root. However, while this is more secure than having no allow list policy and allowing all services and regions by default, this does not drive towards least privilege amongst accounts with different workloads. And so the option that we at Stripe decided on is to have an allow list per OU, for example, a list of allowed services and regions for all accounts in the security OU, and a different list for the infrastructure OU, and so on. This drives towards least privilege by having a more fine-grained control on a per OU basis. Plus, we can still have a base global allow list that's part of each OU allow list policy, which contains the base set of services and regions allowed in all accounts. And this base global allow list lets us make changes more easily to all accounts and provision new accounts instead of having to handcraft the entire set of regions and services allowed per new account. Here's the steps that we followed to create the allow list SCPs. First, we created the initial allow list policies, which contain all services and regions, since by default, everything is allowed. And because everything is allowed, we'll be denying the services and regions that we don't use. We need to analyze several data sources for determining usage, which we'll discuss in more detail in the following slides. With this usage data, we determine the base allow list from the commonly used services or regions across accounts. We also analyze the usage data to determine the additional allow list that each OU needs. And finally, we'll compare the new allow list with the initial allow list and check to see if the changes make sense. Most of the times when you're crafting the allow list SCPs, you're not starting from a blank slate, but rather a cloud environment where you need to keep existing infrastructure up without any interruptions. So at Stripe, we were a bit nervous about creating these allow list SCPs. What if we accidentally denied something that we use? But on the other hand, what if we're overly permissive and continue to allow high-risk services in regions that we have no use for? Plus, there is no automated tool by AWS for this kind of service and region allow list policy generation. And so our solution at Stripe was to develop our own tool to aggregate and analyze usage from multiple data sources. By having multiple data sources, we can gain confidence in our results as these data sources bridge each other's limitations. Also, we use this analysis as a way to pinpoint further the team that's using it and the amount of usage, which is helpful if we want to ask them to migrate in the future to a better supported alternative solution instead. So one important data source for determining usage is CloudTrail. It's a service that logs AWS API calls to S3. You can determine a time period that you care most about usage, such as the last 90 days, and only analyze that time period for least privilege. Some limitations for CloudTrail include that it's only available for most AWS services, but not all of them. And it omits services that are running without recent API calls. So this is why we need to use additional data sources that can cover services that we use but don't have API calls recently for management. One challenge that we had in using CloudTrail to determine usage is how to account for false positives. The heuristic that we came up with for CloudTrail is to differentiate between read and write access, along with the load of requests and checking to see if the request is by a machine or human in origin. For example, in our analysis, we ignore cases of quote unquote usage when people are just curious about a new service and generating a small anomalous load of read requests. And here we have an example log entry for CloudTrail. You can see that the AWS service is recorded in the event source, as well as the account ID and the AWS region. To supplement CloudTrail, we use billing data. AWS cost and usage reports is a feature that logs what services are being used, how much they cost, and in what region and account. While it covers all AWS services that you pay for, it misses free services such as IAM, Access Analyzer, and others. In analyzing our billing data, we noticed that there were quite a few services with an aggregated monthly cost of 0. However, we still kept that data as a cost of 0 may be a false negative in determining usage due to AWS free tier. And the third data source that we use to round out the limitations of CloudTrail and billing data is AWS Config, which is a service that logs AWS resource configurations to S3. It has a data aggregation feature that can be used with AWS Organizations to gather resource data from all accounts and lets you run SQL-like queries. Some limitations are that it's only available for the most popular 40-ish services like IAM, EC2, S3, and it may not support all resource types that an AWS service offers. When we were analyzing the config data, we found that there were some unexpected accounts where a service was being used, and upon further investigation, it was because we didn't ignore resources that existed by default. So our tip is that resources that exist by default, like default security groups, can be a false positive, and it's best to look at other resources for the service instead, like EC2 instances, which need to be explicitly created. We also see here an example for a config resource log with the account ID, region, and resource type, which in this case is a CloudTrail trail. With the union of the CloudTrail config and billing data, we can formulate the service and region Allowlist policies. And finally, we can review our new policies. At Stripe, we went through each service that will be denied, determining what the service does, the security risk for the service, for example, whether it's a data store, whether its resources can be configured to be publicly accessible, whether it allows arbitrary code execution, and more. And based on this, we determine if it makes sense for the service to be denied. And we try to find a balance between developer productivity and security. For example, if it's a free service that's only used for debugging connectivity in EC2 without added security risks, then we can decide to add services to the allow list, even if the data doesn't necessarily indicate that it's being used. Finally, to allow other people to review the changes and which services and regions will be denied, we broadcast this to impacted teams at least 2 weeks ahead. This also helps us gain more confidence that these services and regions are not being used and can be deployed safely. So with our control policies formulated, we discussed some of the risks of deploying them and the process that we at Stripe adopted to mitigate these risks and deploy these policies safely. So there's quite a few risks in deploying SCPs. Our ultimate goal is to have no disruption at all to existing workflows, as we know that if we deny a service that's still being used, all AWS API calls to that service will be denied with access forbidden. First, because SCPs trump other access control policies and the lowest granularity at which an SCP can be attached is at the account level. They have a large blast radius of the entire account being affected. Furthermore, there's no dry run mode available for SCPs, so we can't see what AWS API actions they would block. And in addition, the access forbidden error message that the SCP causes may be difficult to trace back to the source. So the deployment process that we formulated at Stripe is aimed at mitigating all of these risks. First, we make sure that we have clear, easy to find documentation that explains what an SCP is, how to determine the access forbidden message that you're getting is a result of the SCP, how to fix the issue, and other frequently asked questions. We also deployed incrementally with a big time of 1 day, and first deployed to pre-production OUs, then different production OUs, making sure not to deploy to the OU with the most AWS infrastructure first. This allows us to reduce the blast radius for each deployment. And in case of unexpected behavior, we had the ability to do quick reverts by having the SCPs and their attachments to OUs managed in code and separating each deployment into different commits. Finally, we can also monitor for spikes in access forbidden errors via CloudTrail, as well as any incidents that come up regarding access forbidden errors in AWS. With these policies deployed, how do we maintain them and continue to drive towards least privilege? That's what we'll be discussing next, how we maintain the policies at Stripe and our tips and tricks. So as the needs of a company changes and as new projects get launched, it's important that we have a streamlined process for adding to the allow list. First, there should be clear, easy to follow guidance on what AWS services and regions are allowed and the minimal security baseline for operating a new service. It's a bad developer experience if they want to use a new service or region but they just get an access denied error and they can't find any documentation on how to resolve it. Secondly, at Stripe, we have an input form for exception requests to new services with a standardized set of questions and a risk matrix to evaluate those answers. So this reduces the amount of back and forth between the requester and the reviewer and makes it a more streamlined process. Plus, by having this evaluation of each new service, we can determine if there are any additional controls or detections that need to be added for it, such as to alert on sharing a resource publicly. By vetting each AWS service that's allowed through this exception process, we aim to avoid the bad situation of having a security incident where we need to quickly get up to speed on an unknown AWS service that has a high risk misconfiguration. We can also continue to drive towards least privilege by automating the Allowlist policy generation and rerunning it periodically so that the set of privileges can reduce over time as infrastructure may become more standardized and some services are no longer used. This is also useful if there are new AWS services to add to the organization, such as from an acquisition, and we can wait for a period of time to aggregate data and then run the automated policy generation to determine the new region and service allow lists. Now that we've covered the process for reducing the attack surface and how we deployed it and maintain it, we can close the presentation with our lessons learned. So the main lesson to take away is that it's a lot easier to ensure security when we have a centralized point of control using the SCPs to override other access control policies and root permissions, especially in a large multi-account AWS environment, to reduce the attack surface by only allowing use of approved services and regions. Due to the sheer number, it's really difficult to add monitoring and controls on every service and region allowed. I'll recall the illustration we used in the beginning, which is this large periodic table of just a selection of AWS services and how we can remove the security risks of many of these by just denying access to them via SCPs. At Stripe, we were originally quite nervous about the risks of deploying a service and region allow lists in our production environments. But through the policy generation, deployment, and maintenance strategy that we discussed, we were able to reduce the set of allowed policies by we were able to reduce the set of allowed services by over 70%. And so I hope that this is can be a lesson that even though we have these AWS best practices, and they may be quite difficult to actually implement in practice. And this is one case where we were able to use powerful SCPs that allowed us to dramatically reduce our attack surface. And so with that, thank you for listening, and I'll open the floor to any questions.